one item of business before going back to the world of water and its other phases. I just put up this morning the 8th problem set, and since I was so slow doing it, I'm going to postpone the deadline for it to Friday. Canceling problem sets, which I've done in the past sometimes, is just, it's not to your best advantage as it goes. It's helpful to keep having to think about these problems actively once in a while. So anyway, next problem set's due on this Friday at class time. Okay, so what I have been talking about, and we'll finish up today talking about, is the phases of water. To some extent because water itself is so interesting, and to some extent because all the other materials, most of them have these same sorts of phases and behaviors. There are some aspects of water that are exceptional, but the basic idea is okay. So I talked last time about ice, the solid phase of water, liquid water, and gaseous water, or steam, or humidity, or moisture. It's a catch-all. What's the gaseous form of water? It's got a number of names depending on context. And you haven't dealt with these materials, phases, forever, and my focus is primarily on the transitions between them. And so I'll remind you that solid ice and liquid water, when they're together, there's an ongoing exchange of molecules. It's not a passive, inert situation where the ice is just staying there and the liquid water is just staying there. They're exchanging molecules all the time. And I'm sure people have studied this you can tag the molecules by making them radioactive or something. You can watch them move. So you can do stuff like that. But in any case, it's an active place. And when you have the two of them together, they can settle into phase equilibrium at only one temperature, and that's 0 Celsius. I'll come back to a question someone asked in a minute that I asked last time. But basically, if you're below 0 Celsius, or if you like 32 Fahrenheit, the ice grows at the expense of the liquid water. Why? Because the rate at which water molecules break free from the ice at those lower temperatures is decreased. It's harder for the water molecules on the surface of ice to get enough energy by accident, sort of from the neighborhood, to break free and go off as a liquid water molecule. And so the lower the temperature gets, the harder it is for the water molecules to break free. And going cold slows the rate at which they break free. And the landing rate of water molecules on the ice from the liquid stays about the same. And so the balance is no longer equal when you cool down a mixture of liquid water and solid ice. If you go below 0 Celsius, the liquid water shrinks, the solid water grows. You okay with that idea, why it's happening? If you sort of understand it and buy into that concept, that it's a dynamic balance, and that you shifted it off to the side and you broke the balance, you can figure interesting things out all by yourself. For example, if you start throwing stuff in the water, and I talked last time about putting alcohol in, but if you put antifreeze in the water, something that's going to be relevant if you've got a car in the cold weather, if you put antifreeze in the water, you're making it harder for the water molecules to land on the ice. In the liquid phase, the water molecules are diluted. There are not as many of them there right at the surface of the ice. And the other thing is that they're busy sort of paying attention to the antifreeze molecules. They kind of cling to them. And so they think they're not so interested in landing on the ice. And so as you add antifreeze to liquid water, in this mixture of ice and water, you make it so that the landing process is suppressed. So the ice loses water molecules to the liquid, and they're not being replaced. The ice shrinks. You put antifreeze in. If you have a mixture of solid ice and liquid water, pure and simple, they're going to be at 0 Celsius if they're coexisting for any length of time. They've got to be at 0 Celsius. But as soon as you mess up the water by putting in, you can put salt in, you can put antifreeze in, these things that make it harder for the water to land. You're making the liquid water grow at the expense of the solid ice. Yeah, Bashir? Does the freezing point get lower? Yes. So if you keep it at 0 Celsius, the ice is all going to disappear because the landing rate's suppressed. The leaving rate, breaking free of the ice, hasn't changed. The water molecules just leave. And what will happen while this is going on is the temperature will begin to go down because breaking free the water molecules from the ice costs energy. And if no one's adding or subtracting energy to the pot, it's in a thermos or some isolation, you're allowing the water molecules to break free more than in the past. It's going to get colder because where's the energy going to come from to break them free? Well, from the temperature now. So if you add antifreeze or salt to a mixture of ice and water and do nothing else, the temperature starts going down. And yet it still continues to melt, at least for a while. Eventually the temperature gets so low that the rate at which water molecules leave the ice is also suppressed because it's cold. The water molecules can't get the energy they need to break free. So you will reach a new equilibrium, phase equilibrium, but it'll be at a lower temperature. It won't be at 0 Celsius anymore. So any of you who've made ice cream the old-fashioned way, where you mix up the ice and cream and you don't have any liquid nitrogen on tap, so instead you use salt and ice, when you put the salt around the ice, and you can do this on your doorstep when it's a freezy, frosty day and you've got ice out there. When you put the salt on the ice, the salt goes into solution in any water it can find, and now that water doesn't like to land anymore on the ice. So the ice loses molecules to the water, but they're not replaced. So you're forcing the ice to melt. And the ice will melt, become liquid water. The temperature will go down of that mixture because the energy is being gobbled up to break the water molecules free. And eventually it may reach another phase equilibrium. It'll be at a lower temperature. And when you're making ice cream, the beauty of that little activity is that you can end up with a mixture of ice and water and salt that is in phase equilibrium, not at 0 Celsius or 32 Fahrenheit if you like, but 10 degrees colder than that maybe. Cold enough that it will freeze ice cream into ice cream. You okay with that idea? Why adding these chemicals to liquid water forces the ice to melt and also drops the temperature? Questions about it? Okay, so in fact you can force ice to melt into liquid water with almost any chemical that goes into solution in the water. It doesn't actually have to be salt. It can be various, they sell you various other salts other than table salt, but you could use sugar. It's not a great choice. You can end up with bugs. I guess during the winter, maybe not so much. But anyway, you can do it. You can melt it with. What you can't melt ice with is something like sand, because sand doesn't go in solution in water. It doesn't do anything. So it just sits there, occupying space. Okay? Anything else I wanted to say about those? No, you understand not why antifreeze. And the other thing is why antifreeze. You put it in your car. You are making it very hard for the water to freeze, because any ice that appears in your car's cooling system, any ice crystal that's there is going to lose water molecules at the current temperature rate, but they're not going to be replaced very well because the water is busy with the antifreeze and diluted by the antifreeze. Okay. All right, so next balance of phase equilibrium that I talked about was water and gas, water and steam, the transfer of molecules there. And I haven't done justice to that to show you the way it depends on temperature. But it's the same kind of story where water molecules break free of liquid water, go off as gaseous water, and they also do the reverse, back and forth. And it's an exchange. And if the situation is such that water molecules are taking off more often than they're landing, you get evaporation. The liquid water gradually disappears to become gaseous water. And with doing that something has to provide a lot of energy to break the water molecules free of each other and send them on their way. And that is actually a dramatic or substantial amount of energy. And that's called the latent heat of evaporation or latent heat of vaporization. I didn't, again, name the energy that's needed to break water molecules free of ice and make them liquid water molecules. That's the latent heat of melting. Or the formal name is latent heat of fusion, but who cares? So the balance between liquid water and gaseous water. If they're leaving faster than they're landing, evaporation. If they're landing faster than they're leaving, condensation. You've seen them both a zillion billion times. You know that evaporation needs thermal energy. The process of evaporating water needs thermal energy even if the temperature doesn't change. You know this because if you get wet for various reasons and the wind blows across to sort of help evaporation go, you feel cold. You feel the heat being sucked out of you to be used to break the water molecules free of each other and send them on their way. On the other hand, if water molecules condense on you, which they can do, for example, if you put your hand in the jet of steam or steam coming off of a hot pot, that condensation process where the water molecules stick to each other and become liquid water releases that latent heat of evaporation. It's the reverse. And you can get scalded by this. A tremendous amount of thermal energy is released as water goes from its gaseous form to its liquid form, even without changing temperature. The energy comes roaring out. I will remind you of the other phase transition pair, and then I will answer this question that was up here in a second. There was another one coming in too, but the other pair of phase transitions are from solid ice to gaseous water, steam. And those may seem exotic. I've seen both of them actually the past couple days. The process of solid ice turning into gaseous water or steam is called sublimation. That's the name. I can't change it. It is what it is. But it's why you get freezer burn and such. That in a situation where there are not very many landing molecules, the leaving molecules win, and you gradually lose the ice. The reverse process is frost, where the water molecules land so often that they outpace any water molecules leaving the ice, and so the ice grows. And it's technically known as deposition, but you see it around as frost. So where does the white sprinkles all over the grass come from early in the morning? That was just water that deposited right out of the air on the plants as ice. You know it from your freezers too. A lot of you probably have in your dorm room or something like that. One of those the El Cheapo freezer, the little cube refrigerators with a freezing compartment. And as the semester goes by, that freezing compartment gets caked with more and more and more ice. Where does that ice come from? It's magic, right? No, it was never liquid water. It just goes right onto the surface, deposits directly as ice. Okay, so to come back to the first question here, from last time actually, is there a point where all three states, phases of matter, can occur at once? And the fact is, yes, there is what's known as the triple point of water. There is a situation in which the water can exist as solid ice, liquid water, and gaseous water all at once. And they're in stable phase equilibrium with each other. It's just slightly over 0 Celsius. It's like 1/100th of a degree above 0 Celsius. And it occurs when so you think that going to a little bit higher temperature should destabilize the ice, but it also occurs at low pressure. It does not occur at atmospheric pressure. It occurs at about 4 millimeters. It's like 100th of atmospheric pressure. It's actually less than that. It's about a 200th of atmospheric pressure. So at the lower pressure, what I haven't said is pressure does affect the balance between liquid water and solid ice. So you can move the melting temperature of ice in the freezing temperature of water, you can move it away from 0 Celsius by changing the pressure. It's not very sensitive to it, but just a little bit sensitive to it. And so you can get into a situation where the solid ice and liquid water are still in phase equilibrium, and the two of those two things, ice and water, are exchanging water molecules with a very thin steam. That is a steam that has very low density. All three of them are exchanging, and it's all balanced, and it will just sit there. And the triple point of water is useful just as a reference point for temperature. I'm sure it serves other purposes, but it has been traditionally used as a reference point for temperature. Because if you get those three phases in equilibrium at once, we know what the temperature is. It's, okay, just about 1/100th of a degree Celsius. Okay. Why does salt and ice burn your hand when you put ice on your skin and then press the ice on top, or probably the salt on top is what probably was the first stuff. If you have a mixture of ice and salt, there's going to be a little bit of water around too. You are forcing the ice to melt because the water molecules a million of them might leave the ice during this second, but a million won't come back. The salt is keeping the water molecules busy. So you only get 800,000 back. And the result is the ice is shrinking. It's shrinking at a cost. It needs energy for this. It needs to soak up thermal energy from its environment. So the temperature of that system will go down unless it can find something nearby to draw thermal energy out of. And the something nearby is your skin. So if you're holding a mixture of ice and salt, it's going to hurt your hand because it's going to get colder than 0 Celsius, which is already not fun to hold. It's going to get colder, and it's going to be soaking heat out of your hand, and it will. You're holding on to something that's too cold to be comfortable. Okay. What I've left behind and now should talk more about is the balance between liquid water and gaseous water. I said if the circumstances are right that you get more leaving than landing, you get evaporation and vice versa. Well, what are those circumstances? Well, if we pick a temperature, let's just pick room temperature just for fun, because what it is. If you've got liquid water and gaseous, and I've got liquid water all over the place, there's liquid water around. If you've got liquid water around and gaseous water around, which instantly, let me ask this question, just to wake you up. Here's a question to think about here. Not it, that. What fraction of the water, of the molecules in this room's air are water molecules? So I'm sorry to break my trains of thought all the time, but let me ask this one, and I will. Any question of the question? See what you think. I'll give you the 30-second point, and then we'll call it. 3, 2, 1, 0. So we're all over the place. And the actual answer is C-ish. It's about 2%. And how would you know that? It's something that you rarely talk about in. You learn somewhere in K through 12, you learn what the atmosphere is made of, right? They talked about it's almost 80% nitrogen. I've done this too. 80% nitrogen, about 20% oxygen, and a smattering of other things, like a few percent, 1% of all the others, everybody else. Well, what they leave out in that statement, in those sorts, or that listing, they leave out water because they say in dry air, because if you don't say dry air, if you just let the air be, if you count water, now you have to pay careful attention to you have to figure out what circumstance you're trying to describe. If it's really hot and humid, we can be way above 2%. If it's bitter, cold, and dry, you can be way below 2%. It varies a lot, but 2% is about right for our situation right here. That's my point. And so where I want to go with this is like, how would you ever figure this out? And what determines it? Is it just a random thing? The answer is no. So here's the story. There's a significant amount of water floating around this room as individual water molecules, part of everything else I've talked about with pressure and thermal motion, all that. There are water molecules in there. And when I have a container of water around, like this one sitting there, there's a constant exchange of water molecules from the gas, the air, and the liquid water. The presence of the rest of the air, the nitrogen and the oxygen, is sort of irrelevant. The issue is how densely packed are the water molecules, and sort of how often do they therefore have a chance to hit the surface of water and stick. So when in trying to figure out the balance between water molecules breaking free of the surface and heading off into the space above the water, and water molecules in the space above the water landing on the surface, the balance depends on temperature for the water and density for the gas. What do I mean by that? The rate at which water molecules break free of the liquid water is largely determined by temperature. The hotter it is, the more often the water molecules break free. They need the energy they're waiting there at the surface to break free. They need the energy. And they need the statistical they need a lucky break where they get more than their fair share of energy during the random jostling of thermal motion to break off free. And if it's hotter, they're more likely to get that lucky break, and off they go. So temperature determines the leaving rate. So far, okay? The landing rate is determined largely by how densely packed the water molecules are in the space above the water. Whether there's air there or not, who cares? It's just what's up there in the space. And depending on the density of the water molecules, we describe the density of the water molecules in the air with the term humidity. So we could have the air in this room contain twice as many water molecules or half as many water molecules. You would say that the humidity has changed, and it would have certain impacts on you. There would be an upper limit to how much we could put water molecules in this air. In this room, we couldn't put 100 times as many water molecules in there. The reason being that it would start to condense so aggressively. The landing rate would become so huge the water molecules would stick to each other right in the middle of the air, and we'd have clouds forming in here. So right now, I would say that the density of water molecules in this room is not enough to balance, so that the balancing, it's not enough that there is balance between the landing rate and leaving rate. If I've got a pot of water, I feel awkward not having a pot of water in my hand, so I'm going to steal this one for the moment. So at the surface right now, the water molecules are leaving that surface about twice as often as they're landing. The result is that we're gradually losing liquid water and gaining gaseous water. And you might think, well, where did I pull that number? The half. Where did I pull that out of? I pulled it out of the fact that I know what the relative humidity of the air in this room is, approximately. It's actually, I'm guessing it's 50%, but it's actually probably a little below 50. It's probably more like 40. But okay, so what does it mean to have 50% relative humidity? That means that we have 50% of the landing rate you need for these to be in phase equilibrium. There's not enough water in the air right now. So water molecules are leaving more often, the water's shrinking. We're evaporating the water. If we went to higher relative humidity, that would mean that we'd have more water molecules packed in here, in the room. The landing rate would go up, and so we'd be getting closer to phase equilibrium. If we got to 100% relative humidity, now we have phase equilibrium. That's what that means, 100% relative humidity. It means that the water vapor in the air is in phase equilibrium with liquid water. They're coming and going at the same rate. So based on this now, you can, if that makes sense to you, what's relative humidity telling you? It's telling you how far away from the phase equilibrium you're at. And therefore, a number of interesting or useful things. It says how effective evaporation is. As long as you're below 100% relative humidity, there will be evaporation. Liquid water will gradually go away. How fast? Well, if the relative humidity is 98%, that means that the landing and leaving are almost balanced. Evaporation is going to barely work. The water molecules will leave, but mostly they'll return. There will be very little evaporation. It would take forever for a cup of water to go dry. So in situations where the relative humidity is high and you say it's humid today, evaporation is not very good. There's not much evaporation. What are the consequences to you? Suppose you're covered with water. You just came out of the swimming pool or shower, or alternatively, you're sweating. If it's very humid, evaporation's not very effective. It doesn't cool you very well. You count on the animals of all types, including humans. We count on evaporating of water to cool us in situations where we can't otherwise get rid of thermal energy. If it's 100 degrees out, Fahrenheit, that's above your body temperature. You can't transfer heat from your body to the great outdoors very effectively because the heat's going the wrong way. Heat goes from hotter to colder, not colder to hotter. So how are you going to get rid of thermal energy? Since after all, you're making some, just by being alive, you're making 100 watts, give or take. How do you get rid of thermal energy? Evaporate water. So the fact that we can live in environments that are hotter than body temperature is completely dependent on the fact that we can evaporate water. Okay? If the humidity is very low, water evaporates quickly. And with it, it soaks up thermal energy. So in sort of deserty environments, it might be very hot, but it is also very low humidity, meaning there's not much water vapor in the air. So if you put liquid water out, the liquid water evaporates ferociously fast and soaks up a lot of thermal energy. So people cool their houses and environments by evaporating water. You may have gone to some dry place where they sort of spray a mist of water into the air just to make it cooler. That would not, in a dry environment, it works just fine. They make swamp coolers, which is sort of the jargon name for, it's not an air conditioner, which we'll come to down the road. It's a device that lowers the temperature of the room by evaporating water into it. And the act of trying to soak up the water molecules, to release the water molecules from each other, soaks up thermal energy. Okay? Is it possible to have 0% humidity? Absolutely. Make a container of air with no water molecules in it. How do you do that? You use there are some extremely aggressive drying agents, things that soak up water molecules and don't let them back out. You just soak up all the water molecules. I mean, whether you can get down to 0.00000, I don't know. That becomes a statistical problem. Can you find the last water molecule? But you can certainly get down to zero humidity, but to two or three or four decimal points. And in that kind of environment, there's no return process at all. Water molecules leave. There's nothing to come back, at least for the first moments, until you've put some water molecules out there. Going above 100% humidity is hard because the water molecules now are landing faster than they're leaving. They will initially land on surfaces and liquid water and surfaces that might have a little water, but eventually they'll start landing on each other in the middle of the air and form a mist, little droplets in the air. Incidentally, many people, we're used to referring to that mist that comes out of a tea kettle, that's steamy mist. We're used to calling it steam. It's not steam. It's droplets of water in the air. And you see the droplets of water as white, the same way that you see all clear materials. When you crush them finely, they appear white because of reflections from their surfaces. So a plate of glass ground finely is white. rock candy, big sugar crystals are clear, crush them, they turn white. Take water, it's clear, crush it into little particles, it's white. The physics of that is an interesting separate topic. So the steam that you're seeing, or the mist in the air on a foggy day, or the clouds, you're not seeing steam the gas, you are seeing water droplets condensed typically from steam the gas. Steam the gas is clear. You can't see it at all. All right? Yeah, it is what it is. Okay. Well, the balance between the process of landing and leaving of water and vapor, water vapor, it's temperature dependent. Why? Because the hotter you go, the faster water molecules are leaving the liquid surface. And so suppose we want to look at 100% relative humidity at various temperatures. If it's pretty cold and the water's barely liquid, it almost froze, then the leaving rate's very small. So at a 100% relative humidity, there are not that many water molecules around as a gas. Because the leaving rate's small, you don't need many water molecules in the gas to balance it with landing. So when it's cold, even 100% relative humidity air doesn't have a lot of water molecules in it per volume, per liter. If you go hotter, the water molecules, and it's still 100% relative humidity, the water molecules leaving find the energy they need to break free more often, so they leave more often. To balance that, you have to have more of them up in the gas phase to get the landing rate up. So as the temperature increases, basically to summarize this, the higher the temperature is, the more water molecules there are per liter in 100% relative humidity air. We'll get up to, that's good for the moment. So that tells us interesting things about taking the air from outside and bringing it inside and changing its temperature. If you take outdoor air right now, so outdoor air, so go outside, it's cold, we'll assume it's cold outside, and let's let the air be relatively humid outside, meaning that it's got close to enough water molecules in it per liter to be in phase equilibrium with the local water at outdoor temperature. So like the pond, is it the dell? The pond out there. Right around that pond, the humidity is probably pretty close to 100%. The water's landing, leaving, the back and forth. But if it's nearly freezing temperature, it's a slow leaving and slow landing. So the water molecules aren't very dense in that air, even though it's in phase equilibrium with the water. If we take that same air and bring it into this room and heat it up to local room temperature, it's no longer near 100% relative humidity. Because we've heated it up without changing the density of water molecules, it's got the same landing rate as before, but the leaving rate of water that's got the same temperature is much higher. So it's now, that air went from being high relative humidity in the cold environment you stole it from to being low relative humidity in this hotter environment. It doesn't have enough water molecules per liter. Is that okay? An extreme case of this, you go on an airplane. Have you noticed that you go on the airplane, it's really dry there. There's a reason why they're giving you water. There was a brief period when they started to charge people for water. I think they backed off on it because it's just unhealthy. It's really dry air. And so, if you're an opera singer or something like that, you come out not being able to sing your aria quite right. You have to recover. Why is it so dry? Well, it's because they're taking air from outside, and through various processes, they're making it, bringing it up to the temperature and so on for breathing and densifying it and so on. But that air was outside at like minus 50, 60 degrees Celsius or Fahrenheit. They're almost overlap at that point. It was really cold. And that air at best could it be in phase equilibrium with ice. And it would have, if you put together ice and liquid, ice and air, or ice and space, and let them reach phase equilibrium, they're going to reach phase equilibrium because it's so cold, minus 60 degrees, so cold, there's going to be almost no water molecules per liter in that air. So when you bring that no molecules per liter air into the cabin, fix it up all nice for people to breathe, there's no water molecules in it still. It's bone dry, relative humidity like 1. So that's why it's unavoidable. You could think, well, they could humidify it, but they keep bringing it in, throwing it away, bringing it in, throwing it away. They don't want to like carry hundreds of gallons of water, thousands of gallons of water to try to keep humidifying the air. So they try to humidify the flyers. They give you bottles of water. Is that okay? The idea, next time you go flying in a plane and you realize it's like super dry air, there's a reason for it. All right. So, I mean, question. Can you have 100% relative humidity below 0 Celsius? Yes. It will not be a phase equilibrium between liquid water and gaseous water. It will be a phase equilibrium between ice and water. And the relative humidity in your cheapo dorm freezer, in that freezer, it's 100%. 100% relative humidity. There's phase equilibrium between the ice and the gas. No problem. The problem is that it's so easy to go a little bit above 100% relative humidity and grow the ice. It happens every time you open the door. Air goes in with more molecules of water per liter, cools down in the freezer, and now it's above 100% relative humidity. It's got too many water molecules per liter to be in phase equilibrium, so it deposits on the freezer, and you gradually grow ice chunks. So what's the alternative? Well, the frost-free freezers. You know, what is a frost-free freezer? What it does is it deliberately pulls the water molecules out of the air. It makes drier air, less than 100% relative humidity, even at the temperature of the freezer. It does this by letting the water molecules in the air deposit on the coldest item in the entire freezer, which you don't get to touch. It's in the back of the freezer. It's the cooling system back there. They collect the water molecules there, and then the rest of the freezer is a little hotter. So they have the air is in phase equilibrium with a very cold surface, and that means it's got the relative humidity was 100% at that really cold surface, but it's less than 100% everywhere else. And so the air throughout the rest of your freezer and refrigerator system is less than 100% relative humidity, and therefore liquid water in the refrigerator and solid ice in the freezer both lose molecules to the gas. It's dry air. And so the ice cubes shrink, and anything that you got open in the refrigerator, the liquid waters evaporate. All right? So that's what a frost-free freezer is. It's a freezer that has deliberately lowered relative humidity. Any other relative humidity questions you want to ask? Explain the relationship between humidity, density, and temperature. Again, so the humidity of in the air, the vapor, I should say no, the density of water molecules in the vapor at 100% relative humidity, that is when it's in phase equilibrium with the liquid or the ice, is temperature dependent. The colder you have this, so the system has got two parts. It's got liquid water or solid ice depending on where you are along the temperature, you're turning the temperature knob here. So we've got the liquid solid part, and then we've got the gas. And if they're in equilibrium, we're at 100% relative humidity. As we turn the temperature down and we're at equilibrium, there are just less and less water molecules in the gas because we have slowed, with low temperature, we've slowed the rate at which they leave the liquid or solid ice. We have to slow the landing rate. How do you do that? Have less of them. So as the temperature goes down, the density of water molecules in the air or whatever gas you got up there goes down. As you go to higher temperature, now there's more energy around, the water molecules break free of the ice or liquid water more regularly, the landing has to be faster. So you have to higher density of water molecules in the gas. Is that okay? Let's take it to an extreme. Keep going to higher temperature. If we go high enough in temperature, the water molecules taking off are now taking off like crazy. The landing rate has to be ferocious. To balance it, you have to have a lot of water molecules up there in the gas. And associated with a very dense gas of water is an increasing pressure. Because, right, they go together, at least to an extent. You crank up the density of a gas, you get more pressure at the same temperature. But as you go up in temperature and density, you get greatly increasing pressure. What happens if the pressure hits? The pressure created by the water molecules alone hits atmospheric pressure. Up until this point, my stories, it's always been below atmospheric pressure. The water molecules have been sort of like a quiet player in a story. They're not very important in creating pressure. What if they become completely important in creating pressure? They create the entire atmospheric pressure, just water molecules. In that case, first off, you can have a container that is not being smushed by the surrounding air. You can have a container that's entirely filled with gaseous water. And before I talk the whole hour away, let's go to that. I could do it here with a burner. I could do it here and we could watch the temperature go up, and then it would begin to do interesting things that you know of as boiling. Let me do it over here. What I'm going to do is, this is just an ordinary soda can with a little water in it. And at room temperature, this one is at 100% relative humidity because the water molecules had plenty of time to leave and land and leave and land and get the whole thing in phase equilibrium. So this had liquid water in balance with air containing enough water molecules to keep the two happy, liquid and gas. As I raise the temperature, I'm helping the water evaporate, so the landing has to become more aggressive to stay in phase equilibrium. So they're going back and forth again at higher temperature, but they're doing it so fast that the gas above at 100% relative humidity, its pressure has risen, and it is now at atmospheric pressure. And you know, I know this because some of the gaseous water that is steam, and I can not see it by looking in, it's clear, is coming out and condensing in the colder air as droplets and becoming a mist. So if nothing else makes sense, the key point is this container is now filled with water molecules only. Liquid water molecules at the bottom, gaseous at the top. The gaseous ones are managing to be at atmospheric pressure. They're so dense, they're atmospheric pressure, and the surrounding atmospheric pressure outside, atmospheric pressure inside, the can sides are happy. Nothing's pushing on them, no net force. But if I take that gaseous water, the steam, and I expose it to cold surface, which I'm going to do, I'm going to dunk it in this container of cold water, it will condense all the water molecules, or a lot of them, in a jiffy, and watch what happens to the can. I didn't smash the can. Atmospheric pressure did. So in case you missed it, the can is now all squinched. I can do this again. I can do it where I can make it so you can see it. Although I always remember this. I never remember to show it back again. Okay, so now you can see it on the screen. I'll boil the water again. And boiling is where I want to finish with boiling. I'm causing the water to become gaseous. You know, I'm shifting the balance of relative humidity, shifting the balance between water and steam by going to higher temperature. We get eventually to the point where 100% relative humidity gas is entirely made up of steam, entirely made up of water molecules. So we're pretty much at that point again. So again, the container is it's in phase equilibrium between liquid water and gaseous water. And the gaseous water at this point is so dense that it has atmospheric pressure, and it's able to keep the can sides stable against the crushing, potential crush of atmospheric pressure outside. It's atmospheric pressure inside with steam, atmospheric pressure outside with air. But if I cool the steam, it stops being at atmospheric pressure. It condenses quickly. Ready? Get set. You know, thanks. In principle, it's not supposed to be magic. It's supposed to be something you can entirely understand. But I got one more demonstration to do here that I've brought in enough times. I don't want to, you know. Here's the idea. Boiling, we saw a case with a can where if you heat the water hot enough and you get phase equilibrium between liquid and gas, it occurs where the gas is at atmospheric pressure. You can manage to get the steam, the steam at 100% relative humidity to be so dense that it's at atmospheric pressure. Once that happens, you can have a bubble that's stable against atmospheric pressure. So if a bubble formed in this is room temperature, of course. If a bubble formed in this water at room temperature, a bubble of pure steam, its density would be very low. It would be at 100% relative humidity, but its density would be so low, the pressure would be very low. And the crushing atmospheric pressure outside would overwhelm the tiny pressure inside the bubble. The bubble just doesn't have enough steam molecules in there to keep its own against the smush of atmospheric pressure. Well, what if we take, so if you heat the water up hot enough, that temperature, a steam bubble becomes more dense when it's in phase equilibrium with liquid water. So dense, in fact, that it can have atmospheric pressure, at which point it's stable. So at 212 Fahrenheit or 100 Celsius, that occurs. You can have a steam bubble in the water that stays there. It's so dense with hot steam that it's able to fend off the smush of atmospheric pressure outside. And once that happens, water can evaporate not only from the top surface of the water, but also into the bubble, through the surface of the bubble. And that's what boiling is. Boiling is just accelerated evaporation that occurs when you get hot enough that steam bubbles are stable. Once that happens, the steam bubble can, if it appears, it can survive. It doesn't get smashed by atmospheric pressure because it has that atmospheric pressure inside it. And so it's stable, and now we have new surface through which water can evaporate from liquid to gas. The bubble can get bigger. And that's why when you hit boiling temperature and steam bubbles suddenly become stable against atmospheric pressure, the evaporation rate skyrockets. Suddenly you can evaporate water like crazy, so much so that you can't drive the temperature much above the boiling temperature because the energy just starts going into evaporation, not into raising the temperature. What I wanted to show you is you can make water boil at lower temperatures if you reduce the atmospheric pressure. So for example, you go to on top of a mountain somewhere where the atmospheric pressure is less. It's easier for water for a steam bubble to survive there. It doesn't have to be as dense as down here in Charlottesville. So we're going to go up into the mountains, but not just a little, a lot. So three. So we're going to go into a vacuum chamber. So that's just ordinary room temperature water, just to show you. There's my finger. It's so hot. No. Okay? Just fine. No problem. Ordinary room temperature water. But if I take the air out from around, got it? Yeah. If we take the air out from around it, so the atmospheric pressure is smaller, now if a steam bubble forms, it's got an easier time. The atmospheric pressure outside, we're getting less and less of it, there's less pressure pushing in to smash steam bubbles. So if they appear, they got a better chance of surviving. Now, there will come a pressure once we get below a certain pressure, even at this room temperature, steam bubbles are dense enough to survive and grow by evaporation. So the water should begin to boil at room temperature. And it's real boiling. It's the same thing that you're used to. It's just that we have By reducing the surrounding pressure, we've made it easier for the steam bubbles to survive and grow by evaporation. And they're close. Oh yeah, I'm supposed to. This will help. Collecting the water vapor is a good idea. We don't really want to send it into the pump. So liquid nitrogen helps collect the water vapor. So the water's, it's a full boil. It's the same boil you're used to. It's just occurring at room temperature. Because we're, in a sense, we've put the container in a startlingly low pressure environment, way up on the top of the tallest mountain ever imagined. And the water boils at room temperature. All right, thanks. All right, well, more another day.